Let's discuss electrophilic aromatic substitution with pyrrole in this lecture. We have already discussed about benzene and naphthalene, and now we will discuss with pyrrole and very similar molecules furan and thiophene. All of them are five-membered. They have five-membered rings and a heteroatom, something different than carbon here: nitrogen, oxygen, and sulfur. So with nitrogen, the compound is called pyrrole. So we will focus on pyrrole first, and then we will talk about furan and thiophene also. And then in coming videos, we will discuss pyridine and indole also. So let's think about these pyrrole, furan, and thiophene molecules. The pyrrole molecule can be drawn like this. You can see that this circle here can be broken down into these two double bonds, and there also should be a lone pair on nitrogen. And this lone pair should be better drawn inside the ring, right? This way you can see that there are 6 electrons which will give rise to aromaticity in the molecule. And also notice that there are hydrogens at all the carbons, and there is also a hydrogen on nitrogen, which you choose to show or you may not choose to show these hydrogens. So does it have any other resonating structure? Like in benzene, if we talk about benzene, we have one resonating structure like this, and the other resonating structure is you have double bonds at the positions where you had single bonds before. So like this, you can draw two resonating structures. Can you draw another resonating structure for this thing? Can you change the position of double bonds? Then maybe you can try, let's say you want to have a double bond here, but that is not possible because the lone pair is always on nitrogen, and this will be too far from the double bond and it will not allow conjugation. So you can't have a double bond here. Basically, you have only one resonating structure for pyrrole. Well, you can also draw resonating structures by using the conjugation of lone pair and the pi electrons, but then you will have to separate out charges. For example, if I put this lone pair here and take this double bond, these pi electrons on this carbon atom, I will get a negative charge on this carbon and a positive on this nitrogen, and I'll get this resonating structure, but this is not very stable because it has two charges in it. This one is neutral, isn't it? But it has two charges on it. So that way you can draw resonating structures, but not so these resonating structures will not be that important. You can draw, I think, by conjugating, you can draw, as you can see, 5 of them, but they are not important. Let's think about what happens when electrophile attacks the pyrrole molecule. So where can it attack? The first question is where to attack. It can attack on nitrogen. Can it attack on nitrogen? Yes, it can, because the nitrogen here has a hydrogen atom which can get released afterwards, and nitrogen also has a lone pair which can be donated to the electrophile. So the attack at nitrogen is possible. Okay, then also there could be an attack at the alpha position. This position, I would like to call this position alpha, which is right close to the nitrogen, and then there could also be an attack on the beta position, which is right next to the alpha position. So there are 3 positions where the attack can happen. 3 possibilities, right? The green one I will call alpha, and the blue one I will call beta. Let's think about the attack on nitrogen first. What happens if the electrophile attacks on nitrogen? So when it attacks, the lone pair of nitrogen is used, and that is used to make the bond between nitrogen and electrophile, as you can see, and the nitrogen has a positive charge. Now before we had a positive on electrophile, but after the attack we have a positive charge on nitrogen, right, like this. And then you can think this is the intermediate in the electrophilic aromatic substitution, and then you are thinking whether this intermediate has any other resonating structures or not. So you can think maybe that the positive and the lone pairs can conjugate, but if you conjugate them, if you put this lone pair here and the positive charge will now be here, right? And then the nitrogen, but there is a problem with nitrogen. It has become pentavalent, which is not possible, right? So you can't draw any resonating structure here. Even if you take these pi electrons and you want to draw a resonating structure by conjugating this pi electron with the positive charge, you wouldn't be able to draw a resonating structure there also. So only one resonating structure if the attack is on nitrogen. Let's think about the alpha attack now. So I have shown the hydrogen also at the alpha position. Here is your electrophile, which is going to attack at the alpha position, and a hydrogen on nitrogen has also been shown, because because it's not important, you may not choose to do it. But anyways, let's focus on the attack. What happens when the attack occurs? Now the lone pair of nitrogen will not be used. These pi electrons will be used to create a bond between electrophile and the carbon atom, right? So that way you will get, after the attack, you will get this kind of a cation. This is a carbocation, and then you can see that conjugation is possible here. You can conjugate, you can move these electrons here, and you can get this another resonating structure. Then you can also see that you can conjugate the positive and the lone pair of nitrogen. This time nitrogen is donating the lone pair, and N becomes positive with 4 bonds, which is possible. N positive with 4 bonds you will see many times in organic chemistry and inorganic chemistry. That is possible, that there is no problem with that. So now you have 3 resonating structures with the alpha attack. Now let's think about the beta attack. What happens with the beta attack? When the attack is at beta, then you will see that there is a positive charge developing here, and then you can draw another resonating structure by conjugating. If you put this lone pair here, so again you get N positive with 4 bonds, which is possible. So you can draw that resonating structure, but after that you cannot draw another resonating structure, because you might be thinking that these two might conjugate, but if you conjugate them, then you will get a pentavalent nitrogen, which is not possible. So let's remove that, and this time we have only 2 resonating structures. So to summarize, when attack is on nitrogen, you have only 1 resonating structure. Alpha attack gave you maximum 3 resonating structures, and beta attack is giving us 2 resonating structures only, which means that alpha attacks leads to a better intermediate cation than beta attack or attack on nitrogen. So alpha attack should be favored. There is no problem with steric hindrance also. Like in the naphthalene, we had the beta position, which was less sterically hindered, but this time there is no problem with the steric hindrance also. So alpha attack is definitely more preferred in pyrrole. Similarly, in furan and thiophene, they are very similar. These molecules, you can try to draw the resonating structures, you can try to generate the attack and decide and see that in these molecules also the alpha position will be attacked. Okay, so right close to the nitrogen or oxygen or the sulfur, these positions are much more reactive in these type of compounds. So now let's compare the reactivity of these molecules. We have discussed benzene and naphthalene before. Now let's bring in these 3 molecules also and compare the reactivity. About the benzene and the naphthalene, we already know that naphthalene is more reactive. Okay, but now let's shift our attention towards and compare benzene with pyrrole. So in benzene, the intermediate cation has 3 resonating structures, and in pyrrole on the alpha position, which is its best position, it also has 3 resonating structures. And you might say that there is a tie and both of them looks like equally reactive, but that is not the case. Look at one of the resonating structures of Pyrrole. In this resonating structure, there is an extra bond, isn't it? If you count this bond here, there is an extra bond. In this resonating structure, there was a plus charge, and then there was a lone pair here, and in the next one, this lone pair has become a bond pair, a pi bond pair. So there is an extra bond here, and this makes the difference. This is a very good resonating structure, very stable resonating structure, and there is no such thing happening in case of benzene, because there is no atom which has a lone pair which can donate and give an extra bond, give a resonating structure with an extra bond. So that's not happening in benzene, but that is happening in pyrrole. And this makes pyrrole, this one bond is very important, is a lot of energy in organic chemistry. One bond is like 100 kilojoule or 200 kilojoule kind of energy we are talking about. So this is a lot of stabilization, and this makes pyrrole highly reactive, very much more reactive than benzene, much more reactive than benzene. Okay, so what's happening? So let's think about these two molecules later on. Among these three molecules, we can say now that the pyrrole is much more reactive. So it's even more reactive than the naphthalene. In naphthalene also, you don't have such a resonating structure with an extra bond. So pyrrole is much more reactive. And then now let's think about furan and thiophene will also be much more reactive than naphthalene because of the same reason. But then how would we compare pyrrole, furan and thiophene? So let's think about these three molecules. So in case of pyrrole, we know that this was the resonating structure with the positive charge on the heteroatom, which was making the difference. So this is most important for us. So let's think about this kind of resonating structures in all these three cases, with nitrogen, with oxygen and with sulfur. Notice that these oxygen and sulfur will not have a hydrogen attached to them, but nitrogen will have. But anyways, you have a positive charge on nitrogen, a positive charge on oxygen and a positive charge on sulfur. At the first sight, you would say that nitrogen is a group 15 element, while oxygen and sulfur are group 16, more non-metallic element. They don't like the plus charge. Nitrogen also don't like the plus charge, but it's group 15, relatively less non-metallic. So positive on nitrogen is much better than that on oxygen or sulfur. Okay, but then if you compare oxygen and sulfur, a tendency might be to say that the oxygen has a smaller size and the sulfur has a larger size. So in sulfur, you have a positive charge which is distributed at a larger space and it's more stable. But please think about how this bond has came into existence. This bond was before the lone pair of oxygen and the lone pair of sulfur. And the lone pair in oxygen is in 2p and the lone pair in sulfur is in 3p, or equivalent orbitals. So that way the sulfur will not be able to donate its lone pair easily to carbon, which has 2p or equivalent kind of orbitals. So keeping that in mind, the donation of lone pair from sulfur is a little bit difficult. Nitrogen also has a lone pair in 2p, so it can easily donate and it can handle the positive charge also better. Keeping these three things in mind, one can understand that the stability of these three species is in this order: nitrogen bearing the positive charge, that is most stable, and sulfur bearing the positive charge is least stable, which makes the reactivity order like this: first thiophene, then furan, then pyrrole, and before that you have naphthalene, and before that you have benzene. Okay, so this is the case till now. We will discuss about pyridine in our next lecture, next video. Thank you very much.